Hey everybody, what's up? We are going to talk Conic sections applications today. And so I'm looking at Conics Packet 2, I guess it's page 11, and we'll just try some of these word problems together. And what I'm hoping is it's really good review. We'll use our skills with figuring out features of ellipses, parabolas, hyperbolas, circles to figure out how to solve these problems about everyday life. Take a look at the top and just look at that picture for a second. Before I forget, I got a submission of a joke from one of you. And I hope I get the wording right. The joke was, hey, have you guys been to the new restaurant? It's called Karma. They don't have any menus. You just get what's coming to you, or you get what you deserve. It was something like that. So thank you for that submission. Take a look at these pictures at the top of page 11. Do they remind you of anything from everyday life? If you were to take an ellipse and spin it round and round over its major axis, you would get an ellipsoid. Same thing with this hyperbola. You could take a cross-sectional hyperbola, put it in motion around its transverse axis, and you get a hyperboloid or a paraboloid that you see here in 3D. I don't know, what do these things remind you of? Maybe like a football or a rugby ball? This could be like, I think of The Simpsons, those like towers of the power plant factory. A satellite or the inside of a flashlight. A lot of these you're going to see coming up in everyday life. So let's look at the first one. It is talking about a satellite. It says a satellite dish is shaped like a paraboloid of revolution, a surface formed by rotating a parabola about its axis of symmetry. And the signals of this parabola, lots of times when you talk paraboloids, if it's a flashlight or if it's signals from a satellite, the focus becomes really important. The focus is what these rays are going to bounce off of. And it says they strike the surface of the dish and they're reflected to a single point where the receiver is located. That must be the focus. I got to think about that. If the dish is 8 feet across total at its opening and 3 feet deep at its center, at what position should the receiver be placed? They're asking you, what is that focal point? Well, what I think is going to be pretty cool about problems like these is we can make the parabola work for us. That is, we can set it up conveniently so it has a nice, easy vertex. I'll have this opening up, vertex right at the origin, right? Oops, have that there. And model it with an equation, right? We'll use an x squared if we're saying that the parabola is going to open up. So I'll use x squared, and you're right at the origin, so no h, equals 4p, that's what we got to find p so we can get to the focus, times y minus 0 as well. That would be one possible model of this. And then we got to get p. What do we know? We know that we know a couple points because of symmetry. We know a couple points on this parabola model, right? The whole width of that satellite dish is going to be 8 feet. So going over halfway is going to get us to 4. And coming up, right, it looks like this axis can, on the axis of symmetry, we can be 3 units up. So you have by symmetry actually 2 points on this parabola. And I'll just use one of them. I'll use the point 4, 3. So we'll plug in a 4 for x, so we get 16 squared. We'll plug in a 3 for y, so times 3. And then, oh, not 16 squared, right? Just a 16. 4 squared, getting ahead of myself. 16 equals 12p. And we'll reduce, we could say p equals 16 over 12 or p equals 4 over 3. That is the distance in feet that you have to travel from the vertex to get to the focus. So tell them to put the receiver 4/3 feet, maybe out from the vertex. And then you're on the focus. And that could do the trick. All right, let's look at the second one. Ellipses also have this reflection property. If a source of light is placed at a focus, the waves will reflect off the ellipse and concentrate at the other focus, because ellipses have 2 of them. This is the principle behind, I don't know if you've ever been to a whispering gallery, and there's one in the Museum of Science and Industry in Chicago. If you've never been to Chicago, highly recommend it. And one of the cool stops there is this crazy museum. We have the dimensions of the whispering gallery in this museum, and it's supposed to be shaped like an ellipse. So checking out the info that's given, again, let's make this problem work for us. Let's just decide that we want the room to be this top half of that ellipse, and you have the 2 foci. I'll put them right along that horizontal major axis, and we'll use the dimensions to see if we could label this up as a model. The whole whispering gallery is 47.3 long horizontally, so you can cut that in half and get to one of your major vertices here. Half of that would be a 23.65 feet. Over here, if you want to label by symmetry, because of how we modeled this, you're at negative 23.65. And then I think we have C as well. Center to focus is going to be 20.3 feet. So you're 20.3 feet horizontally positive this way and negative 20.3 feet the other way. So we know a little bit about that picture. I bet it says find an equation that describes the shape of the room. How high is it at its center? It'd be good to know A, B, and C. So here from the picture, A is center to vertex, 23.65. C is center to focus, 20.3. And with ellipses, you've got A squared equals B squared plus C squared. So we can plug in the values. 23.65 squared equals B squared plus 20.3 squared. And we get B squared equals, do a quick calculation, around 147.2325. Now this is not exact, but it's just a model anyway. So for now, it'll be good enough for our equation. So we're going to put this into an equation just to answer the first part of the question. We've got, we're centered at the origin, so we can model it with a numerator of x squared over a squared. So over a squared, we can say, I'll just actually write it, 23.65 squared plus, with an ellipse, y squared, y minus nothing squared, over roughly that amount, 147, maybe I'll round to 233, how about 233, equaling 1. Should do the trick for a nice model of the shape of the room, and it should help us answer questions about the room. How high is the room at its center? Well, once we got the B distance, that'll help us with the height of the room, right? The half of the length of the minor axis. So use B to get this answer. B is going to be the square root, about the square root of 147, 147.233, and B is roughly 12.1, rounding to the nearest tenth at the end. So the Whispering Gallery is about 12.1 feet tall using the model. All right, at the bottom, another ellipsoid, an ellipse that's revolved around its major axis. And this one's talking about reflectors of sound, light, and other waves. If we place a signal at one focus, the signal reflects off the elliptical surface to the other focus. So just like that Whispering Gallery question. This property is used to make mirrors for optimal equipment, study aircraft noise and wind tunnels, and it's used in healthcare to avoid surgery and treatment of kidney stones. So this diagram is supposed to be something called an elliptical lithotropitor, which emits underwater ultra-high frequency shock waves from one focus with the patient's kidney carefully positioned at the other focus. I bet you never thought that foci would become such a focus, or should I say just so important in a lot of these everyday life situations. The ellipse used to generate the ellipsoid of the lithotropitor, so you're talking about a cross section of this ellipsoid, has a major axis of 12 feet and a minor axis of 5 feet. I bet the math won't be too tough here. It says how far from the center are the foci. This reminds me of something that has to do with A, major axis. This reminds me of something that has to do with B, and focus to center needs to be something that has to do with C. So let's say A is half the major axis, 6 feet long. B is going to be half the minor axis, so 2.5 feet long. And we'll use what we know about ellipses, right? This one's longer than it is tall. We'll say A squared equals B squared plus C squared. So 36 equals B squared, so 2.5 squared, 6.25 plus C squared. And we get C squared is 29.75. And C is going to be roughly the square root of that, so we will round in a lot of these. We'll say 5 points, how about just 4 or 5? We'll put units on it. It's going to be feet. So just the dimensions of the major and minor axis of that cross section helped us go in and get where the foci should be placed. Okay, lastly, on this page, I just want to give you a little bit of advice for what I think is a tougher hyperbola question. And part of the reason that 4 and 5 on this page are going to be tough is even just recognizing that they're talking about a hyperbola in the question, because they never mention the word hyperbola, nor do they mention hyperboloid, like the other ones have been saying the 3D shape. And this isn't about a 3D shape. 4 and 5 are more about the path of either sound waves or light waves. And you're supposed to know that this is a hyperbola question because of the way a hyperbola gets constructed. I would recommend first reading through the problem here, and let's see if we can give ourselves a big space to graph this one. I notice in 5 they already provided the graph of a hyperbola for us, but in this one we'll make it for ourselves and see what they're asking. Suppose two people are standing 1 mile apart and they both see a flash of lightning. The easiest thing to do would be to put those people along the horizontal axis or the transverse axis of the hyperbola. After a period of time, the person standing at point A hears the thunder. 1 second later, the person standing at point B hears the thunder. So we are due west of one another and we're horizontally apart. Let's put A, I'll just choose A to be over here and B is going to be there. So B is to the west, right? We'll put B there. And they're standing 1 mile apart, but what we're going to use in this problem is the speed of sound, and we're going to use it in feet per second. So can you put that at the top? Speed of sound. And the textbook and WebAssign generally uses 1100 feet per second. So I'm already noticing a mixture of different units in this question. And we might as well say instead of 1 mile apart, let's put that in feet. And we'll say that A and B are going to be 5,280 feet, which is 1 mile apart from one. All right, now there's this strike of lightning that person A hears 1 second before person B. So if I'm choosing to put the lightning somewhere up above these 2 points, I'm going to pick a point that's a little closer to A than it is to B. I'll just draw a little lightning bolt there. And what we want to do is the difference between the time that each of these people hears this sound is going to stay a constant 1 second. And this is how we know this is going to be a hyperbola question, because the way that we constructed a hyperbola, even without seeing a graph, the way that we constructed a hyperbola was that we kept the difference between the distances from a point on the hyperbola to 2 points called the foci constant. It wasn't that the sum of those two dotted distances were the same, it was that the difference of those two dotted distances was going to stay constant no matter where you slid that point along the hyperbola. So we're getting through some of the craziest parts of just the setup of this diagram. We know the center of this hyperbola is at 0, 0. So if we thought it might be useful to start writing the equation of a hyperbola, we've got, the way we set it up, we've got our numerators all set with the minus in between and the 1 on the other side. Do we know A and or B and or C? That's the question. We do. We know half of 5280 is going to be C, center to focus. So somewhere down here at the bottom, where it would be convenient just to put some useful info, we can say C equals half of 5280. So C is going to equal 2640. That should help. If only we knew A or B, we could get the last of the 3, and we do. One thing we haven't used yet, I want to come back to the speed of sound travels at about 1100 feet per second. That's important. It took 1 second, right, of time for person B to hear the lightning after person A had already heard it, and 1 second of time at that rate means in that second, the sound traveled this distance. It traveled 1100 feet. 1100 feet is going to be the constant difference between those two values. Well, what does 1100 have to do with anything in the picture? Well, imagine sliding that point down right on top of the vertex. The difference between this whole distance and this little chunk of distance has to be that constant 1100 feet. And really, if I took this whole thing, vertex to B, minus just this little vertex here to A, what you would get would be the length of the transverse axis. You would actually get 1100 feet. So 1100, that difference, right, if is going to be 2A. And we're going to say A would be half of that, 550. That's another crazy part, but it's going to help us in our quest to get B. All right, so it's time to get B, right? No time like the present. We know with hyperbolas, we can use regular Pythagorean theorem. So C squared 2640 squared equals A squared plus B squared. Solve that for B, you get B squared equals, don't be scared, 666, that doesn't look great, but then 7100 on the end of it. And that can go with the y's. X's can be A squared, so 550 squared, and then B squared can go here. And this is going to be a usable function as a model for where this lightning's going to fall. Sometimes that's the end of the question. I'm going to run out of time here. They actually ask you where did the lightning strike occur, and it says it's due north of point A. Since A is at 2640, 0, my advice is plug in a 2640 for X, solve for Y, and you'll see that you get 12,122 feet. See you later. Have a great day.